All right, team, what we're going to look at here is rolling with friction. So we're going to do a couple of experiments to start out with some things to see where you're at. So we're going to talk about pushing on a big wheel like this. So this is my reference. So what's going to happen when you push at different locations, we want to find out. So we're going to do an experiment here that you should be able to test it out. So let's start our experiment here and see what you have. So the first setup, I'm going to look and say, all right, what happens when I pull this way right at the bottom? Okay? And we want to know what happens if there's no friction. So I'm going to lift the wheel up and then pull, and we want to see what's going to happen. So you should be able to make a prediction about that. So let's test your prediction now. I can lift this up, and I pulled, and you can see which way it rotated. There. Hopefully that matched your prediction. If not, go back and change it. Let's look at the next spot. What if I pull, again, here's my axis of rotation, if I pull right at that axis of rotation? Again, make your prediction. Pulling, nothing. Okay, so hopefully that was your prediction, right? And why did it do that? Why was there no rotation? You should be able to tell at that point now. Last one. Let's look at the top. What happens if I pull from the top here? Okay, again, with no friction. Okay, so if I'm going to pull right here this way, okay, once I lift it up, what's going to happen to the rotation? You should be able to answer that question. Okay? So you can see when it's up here, okay, at this location, when I pull, you can see there's some rotation. Right? So now we want to look at, let's see what happens when I have friction. Okay? So now I'm going to leave the bike down. Okay? And so I'm going to start here. Okay? So I'm going to pull here. Now we just saw when you pull this way, the wheel should go, essentially have backspin on that. But let's see what happens when we have friction. Okay? So, weird. I wonder what force must have done that. What force can be parallel to the surface? It's not tension, because tension makes the wheel go this way. But if you notice, as I pulled, the wheel rotated forward. Okay? So that has to be another force. It's friction. All right. What about in the middle? On this one, we saw if I pull really hard, I'm pulling like as hard as I can, I'm getting a good workout. It doesn't rotate. So there has to be some other force causing this to rotate when I pull on it. Okay. What made the wheel rotate? Okay. Again, that force has to be friction, and this is what this whole video is going to be all about. Okay, last one. So here I pulled here. We know that already makes it rotate. Okay. So we're going to learn about things. Do I need friction? Now you can't tell this unless I guess you get your kid brother's bicycle and put it on the kitchen table. Would not advise against this. Okay. Would not advise for that. But as I do this, okay, as I pull, it goes. I'm going to tell you, it was pretty easy to pull. I didn't need a lot. Okay. When this was down in the middle, right, I had to pull a little bit more. Or at the bottom, I definitely had to. And as I go here, definitely took some more of a tension force to get that started. And so that's what we're going to look at in the rest of this video. All right. So now let's get into look what happens if you push with no friction. So we'll do again a quick setup of what happened. So Let's do if you pushed. Before we do that, let's come down to here. So here, let's draw a free body diagram on this thing first, and let's say, so we do this. So free body diagram, gravity always acts at the center of mass. Normal force is perpendicular to the surface. Right? So there's my surface, and it's touching right there, and it goes perpendicular. Sorry, it's trying to be a straight line. I got to work out from all that tension force. And then now, what other forces are there? So let's say you push. So we'll call this an applied force at the very bottom, where I did the tension with the wheel. So I was pulling here with my rope, okay, that direction. Okay. Now, again, no friction. There's no parallel force there. Right? So we want to see what's going to happen. Right? And the reality is gravity does no torque because it's going through the axis of rotation. Right? That force line, how far is it from the axis of rotation perpendicularly? The answer is 0. Okay? So it has 0 torque because torque equals F times lever arm. The lever arm is the distance from the axis of rotation to the force line, the perpendicular distance. So if they're touching each other, that distance is 0, so no torque. However, right, if I look at this one, right, I now have a perpendicular distance from that axis of rotation to that force line. So there's my lever arm. So this creates a torque, right? And it creates a torque going that direction. So on that one, we should have gotten a, what is that, counterclockwise torque. Let's go back up to here, what happens, right? So if I push here with the red, okay, I should have had backspin, okay? And so that was called slipping, because non-slip is when this is essentially our non-slip equation, is when those balance. And so what would be my linear motion? Remember, F net equals ma. In the x here, we're only going to focus on x direction for motion, so that would be my force of tension equals mass times acceleration. So this would get me an acceleration to the right. But to have my angular acceleration match that, it should go that direction. They should be moving together without slipping. So there we have some slipping. So this equation isn't valid if that's the case. What happens if you pushed right in the center? Well, you saw this. If I push right in the center, okay, there's my axis of rotation. That force line goes right through it. So then my acceleration, my angular acceleration would be 0. It wouldn't rotate. But if I push right there in the middle, I will also have a linear acceleration following this, F equals ma. What if I pull at the very top? Okay. Again, if I pull at the very top, I'm going to get a linear acceleration, but I'm also going to get an angular acceleration clockwise, so that matches. So at the top, maybe I don't even need friction. Okay? So I'll tell you, friction's purpose is to make sure this equation works. Okay? Alpha times r, or the non-slip equation. Okay? So its goal is to make the non-slip equation valid. And so what we'll do is we can again go back through and look at some of these. So what happened when I pulled there at the bottom? Okay? If I pulled at the bottom, we know I have to the right, we're going to call that a positive acceleration. And if I pull at the bottom, I then also have an alpha going this direction, but they're the wrong direction. So one is positive, the other one is negative. So this equation here, I got a negative on this side and a positive on this side. Now friction says, no, 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 we're going to fix that. So friction has to fix that. So what friction is going to do is try and make this negative. And then in this case, it's also going to try and make this positive. Right? So where would friction go to make the rotation then be positive? Right? So friction, again, it's parallel to the surface, so it can only be right or left. Okay? So if I make it to the right, that's just going to make it more negative because I'm even trying to do more counterclockwise torque. So here, friction has to be going this way, and that's what makes the wheel then actually rotate, like you just saw in the experiment, or it will slow down this negative one. What about that? Is friction also trying to make this negative? Is friction now slowing down that positive acceleration? Yes, because now I would have Ft minus force of friction for my net force. So maybe friction is going to be larger than that force of tension. Okay, and you saw the wheel move to the right, so it didn't make it completely negative, but it tries to balance it out. And so now you can see that friction actually had enough torque to make this thing rotate. Then maybe once it rotates, friction can change from there. But friction's whole goal is to make sure that equation works. Let's talk about friction. This is very important. Friction with rolling friction is static friction. So remember, force of friction static is less than or equal to mu Fn. And you're going to see some other stuff in the energy video about this. But the huge thing, it's static because this force, as I push this way, this point doesn't slide as we're doing this. So what happens is it's not, I don't know if I can show you this, it's not this sliding. What's happening is it's rolling as we go. So that point here at the bottom doesn't slide along, so there's no rubbing along. All it's doing is it takes it and turns the thing. So that force of friction, that molecule here doesn't move and slide like kinetic friction. Essentially, that friction just makes the particles move up and down. So really, all static friction does is changes direction, not speed. And that's really important for work in kinetic energy, which you'll see in the next video. So here now, we can then go and try to apply some things here. Again, if I push at 1 meter here, so it says the radius is 2 meters, and if I push at, normal force goes from the ground, gravity goes all the way down, and I'm going to push here, right? Or pull there. So again, that should create a counterclockwise torque, right? And the only reason Ft does any rotation is because it's going the opposite way. But now friction will fix this, and friction will go the opposite direction because it has to balance out that non-slip. So friction goes to the left because this thing, if you push to the right, the wheel is going to accelerate to the right. So then friction is there to say, all right, we're going to make sure it rotates that direction. Again, only friction and tension have lever arms, so they're the only ones that create a torque. So now what we can do is we can look at this and try to solve some problems with it. So I decided to type in an explanation for you guys on this one instead before moving on. So I wanted to let you understand what's happening. In this example, when we pulled low, force of tension has a lever arm, and so it creates a counterclockwise torque, which we have it going right there, this direction. And it has a lever arm, so it can create a torque. Now friction, there has to be a clockwise torque to prevent slipping because alpha times r equals A. If this is going to the right, then the angular has to be going with that. So that's how they would move together without slipping. Right? So there has to be some type of clockwise torque, and friction would create a clockwise torque, but it's the only force that can do that, so that's why it has to be going to the left to create that clockwise torque. Let's look at the other two locations and see what they have. Right? What if I do right in the middle? Right? If I go right in the middle, is there any rotation? Right? And the answer is there's no rotation then. Right? But if I have a linear acceleration to the right, I have to have this clockwise rotation, so friction is still going to go that way. It's not going to have to work as hard because it's not fighting that reverse torque, essentially, of tension. What if I push at the top? Okay, what if I push up here? Okay, so if I push there, I have my same linear acceleration like I've had in all of them. And then this force also creates that torque that way. So hey, maybe I don't even need friction if those are matching up. Depends on how hard you're pulling and things like that. But that's what we'll look at instead of other calculations, is find out, well, is there a limiting point for finding out if I need friction or not? All right. So do I need friction? And at what location could I pick where I need friction? So again, this is a systems problem. So again, relax, free body diagram, what matters, okay? We don't have to worry about gravity. We don't have to worry about normal force because those are in the y direction. And then they also are not creating torques. So let's do my F net equals ma. So I have force of tension equals mass times acceleration. Then my torque net equation. So the only force right now creating a torque is tension times this lever arm, whatever distance, we don't know that, equals I alpha. And again, we're trying to find L. Right? The problem is now we have all kinds of things we don't know. I don't know Ft, I don't know A, and I don't know alpha. We're saying we know M and I, which we'll see in a second. So we saw the third equation you need is A alpha times R equals A. So I can merge these two together. So I could say alpha equals A over R. So that's how you get these two equations to speak to each other. So now this equation becomes A over R. I just plug that in right there. So now a little bit more. Okay? So now what you can do is here you can just do some essentially math and plug these equations. So let's take this Ft and plug it in right there. So now I have Ma times L equals Ia over R. From there, I need to plug in what I equals. Right? So what we could do from this, I went to that rotational dynamics page, and I want to look some more about rotational inertia. Remember, a point particle is mr squared, but we want to talk about these. Now, you would always be given these, but roughly it's just understanding where that mass is put in terms of axis of rotation. And so here, all of these have mr squared with them, and they just have a fraction in the front. So this one, the fraction is 1. So essentially it's saying 100% of the mass is at the radius for a hoop, where a cylinder is essentially half of the mass is in front. So what you would substitute in for that would be kmr squared, what I substituted in for I. So again, the K is the percent of mass at the radius. That's one way you could look at it. Right? Just think about it. If I have more mass at the outside, that's going to be a higher number, and the highest it can be is 1. So then this is A over R equals MAL. So interesting enough, my masses cancel out. They're on both sides. My acceleration cancels out. So I have L equals, and one of these would cancel that. So K times R. So that lets me know where I have to push. And it depends on the shape. Okay? So if my K is a hoop, Okay? So a hoop is just mr squared, and you'd be given all of these. So that means my k is 1, so I would have to push at the radius to not have to worry about friction. What if this was a disk? Right? If that is a disk, then a disk is 1/2 mr squared. So if it's a disk, is easier to rotate, so I could push lower. I don't need as much torque. So again, conceptually, just understanding where you could push, I don't need as much forward torque with a disk, so then I could push lower. So that's kind of what that one looks like. So again, the big piece is I really think conceptually is what's going to get you by on how these things work. Right? So I'll show you the math on the next one. I don't think they're going to ask you to do that, but they would ask you to maybe draw the free body diagram. So this would be a setup of how it would all work. So I'm given all this information. How far will the tire move in this amount of time? So again, we know gravity is going down. Normal force is going up. We're pushing, the radius is 2, so we're pushing below at this location. So then where would friction have to go? Well, I have a forward acceleration, so I need a forward angular acceleration to go with that. This tension would cause it to go the opposite way, so I need friction to make this thing rotate forward. So there I have friction going backwards. So then how do you get to doing all of these? Well, just like before, free body diagram, F net statements, Ft minus force of friction equals ma. Torque equations, again, we're making forward positive, make the direction it actually moves positive. So then I here have force of friction times the radius, because that's where its lever arm is acting, minus force of tension times its lever arm, which is going to be a smaller amount, equals I alpha. Then we use the alpha times r equals a equation to match those up. One huge question is, can you just say force of friction equals mu Fn and plug that in here? And the answer is no. Remember, this is static friction, so it's less than or equal. Friction only has to use as much as it needs. And so we don't know how much that is. So that's a huge no-no, is plugging that one in there. You do not know that amount. If you want to solve friction, you have to use this equation. So now what I could do here, if I'm wanting to know how far it goes, that's linear. So I want to get rid of angular values. So angular equals linear over r. And so my equation's getting closer to do it. Now I'll show you a cool math, because it may be good for in the future. But if you don't care, you wouldn't be asked to go this farther method. But that's kind of the ways you could do. So if you don't care, you could stop the video. I won't ask you to do full calculations. I would ask you to probably go about this far setting up your equations, but no more. So let's show you the whole thing, though, if you're interested and want to be prepared for college physics if you end up having to take it again. So here, I like to just merge some equations. So I want to get rid of the force of friction here, because I know my force applied. I know how hard I'm pushing, so we're calling that tension here. So I know that. I know the radius. I know the lever arm. I know the mass it gave me here. I know I right here. So these are all my knowns. So I'm looking for acceleration, so I have to get rid of friction. So you could do an ugly equation, okay? And what you guys could do, this is what most people do, this is what I used to do until I found this really cool method, is I set that first equation and I said force of friction then would equal Ft minus ma, and I would plug that into here and get huge algebra. So if you're good with system of equations, you can do some fun things. Because I could just subtract these two. Okay? Because if you notice here, I have force of friction on this one, and a negative force of friction and a force of friction. So maybe not subtract, maybe let's add these two, because I have negative and force of friction. But to do that, this has force of friction, this has an R in there. So what I could do to get rid of that is, why don't I just divide everything in this bottom equation by R? So divide by R, divide by R, divide by R. So now that cancels out, so it's looking a little bit better. So let's now add these two equations. So then I would have Ft plus, down here, let's say Ff, because those R's canceled out. Then I have my minus Ff at the top, and then plus a minus Ft times L over R equals Ma plus IA over R squared. So here, those two things canceled out. So now I have Ft minus Ft times L over R equals, I could factor out my acceleration, and then I have mass plus I over R squared. So from here, you have all the values, and you should be fine to do this. If you looked here, how can I add a tension and a tension times something? Well, tension is measured in newtons. This is newtons times meters over meters, so those cancel out, equals an acceleration. And what is this? I have a mass, so that's kilograms. I is kilograms times R squared. Remember, it's just kmr squared over R squared. So those cancel, so it's again another mass. So this is totally valid. And so that's just a cool way you can practice with your algebra to do that. And so solving your acceleration. From there you could then go, having that acceleration, how could I get rotations? Well, angular times R equals linear, and you could do that. The very last piece is, what is the minimum coefficient? Well, remember, at minimum coefficient, minimum mu, that means I need all the friction. So then you could do force of friction is less than or equal to mu Fn. If I use all of the friction, then I'm the greatest amount. So then force of friction does equal mu Fn. So you could have solved for friction up here, because once you know the acceleration, you could go back to this equation. If I know this acceleration, I know this, I could go and solve. So there's a cool way how to do that.